Hey, welcome back to Famama Physics. In this video, we are going to look at 6.2 part 2. Now that we know Newton's universal law of gravitation, we can now use this force to look at the required force we need to keep objects in orbit. Remember, for circular motion, when the centripetal acceleration is towards the center of the circle, in which case, if an orbit, it's towards whatever massive object is in the middle, that means the direction of the force in pointing into the circle will be the force due to gravity acting on that object in space. For satellite, it is the weight that it's experiencing, which we can use Newton's universal law of gravitation to figure that out. Same thing with orbits of moons, planets around the sun, and even galaxies and black holes. We use a similar model, but it gets a lot more complex. When the gravitational field is so strong, we get all sorts of time length dilations. General relativity starts to kick in, which we can't even use this kind of model anymore. But for simple cases, we can, for us. Okay. Example 2. We missed example 1? Okay. No, example 1. Example 2. Okay, let's start off here with a satellite weighs. Ooh, okay. So I might have to change some wording here because it's a little funny. So satellites weighs 9 times 10 to the power of 3 newtons on the Earth's surface. So I'm assuming that's the Fg value. How much does it weigh if its mass is tripled and its orbital radius is doubled? I guess this question is really asking for is what happens to this object if it's a little bit further out. If it's further away from the center of the Earth, what is the force due to gravity? So we're looking for Fg again, compared to if it's on the surface of the Earth. So we'll do a comparison and we'll see kind of what we have to do here. So we know that Newton universal law of gravitation is big G, big M, times small m over the distance from the center of the Earth squared. Okay? So we know that the original Fg is this value here. So if we go up to somewhere further away, let's say we triple the mass. So this here is tripled. Okay? The radius is doubled, so it's even further away from the Earth. So imagine this is doubled, okay? Notice I put the brackets in there. So if we have to figure out what factor of Fg does it, if we find out the fraction compared to the original Fg, then we can figure out what fraction of this value we have to take to get the new weight of the Earth, of the satellite. So it seems as if that this 3 is on top. So if we triple the weight, if we triple the mass, we're definitely going to triple the weight. Okay, so that's going to be a factor of 3. We're going to multiply this by a factor of 3. However, we're going to be further away from the Earth. So it doesn't scale linearly. It doesn't scale directly inversely with the distance. It squares the force due to gravity is directly proportional to the inverse square of the distance. Meaning, if you increase the distance away from the Earth, the force due to gravity will scale down drastically. So this is not just to the power, this is not just by a factor of a half, but it's a factor of a half to the power of 2, which is 2 to the power 2 is going to be 4. Okay, so this is 3 over 4 times the original force due to gravity, okay, compared to before. Okay, so 3/4 of 9 times 10 to the power of 3. So we'll do that right now. 3 over 4 times 9. Oopsie, this should be in green. Times 9 to the power of 3 newtons. And putting that into our calculator, I'm just going to do 9 times 3 over 4. That's going to give us 675. So 6 750 newtons compared to before. Okay, so that's kind of like doing like a ratio test. It's like a proportionality. This is basically, this question is testing you whether or not you know what is directly proportional to what. So for mass is directly proportional to weight. However, the distance of separation is it's proportional to the inverse square of it. So you're gonna lose weight, Fg, drastically if you go further away from the center of the earth. Okay, that was example 2. That's all there is to it. So I thank you for watching, and I'll see you back. We'll hopefully talk more about examples related to orbits in the next one. And see you next time, Fan Mama Physics signing out.